Good morning one and all. I welcome all the MPCS second year students to the online classes. The summary of last lecture that we have discussed about transverse impedance. I have finished the first part of first unit of waves, that is about waves produced in strings. The second part, today onwards I am starting the second part of waves unit, that is waves in bars. So this is the unit 1, second part of unit 1, that is waves in bars. Waves in bars. This is the second part. First part is about strings, second part is about bars. And remember, in first part, very important long questions. First long question is energy modes of vibrations in string. That is a very important question. Modes of vibrations in string, energy density, energy transport. These are the three important long questions. Clear? Out of these three, modes of vibrations is a very important long question. Second one is energy density. And coming to the short question section. Short question section, transverse loss in stretched string, first short question. Second short question, very important short question, velocity of transverse wave in string. Velocity of transverse wave in string. Transverse loss in stretched string. One more short question, that is transverse impedance, that is calculation of Z. These are the three short questions. So you have to read all these important questions so that you can attend perfectly in the annual examination. Coming to the second part of this waves, that is waves in bars. So this second part is also classified into two parts. One is waves, longitudinal waves. Longitudinal waves in bars. Second part is about transverse waves. Transverse waves in bars. When a bar, a rod, how do we define a bar? Before that, how do we define a bar? It is a uniform thickness. The uniform thickness made with homogeneous isotropic material. A uniform material made with homogeneous and isotropic material when its length is more compared to its thickness is taken as a bar. When length is more when compared to its area of cross section, this is area of cross section. When length is more when compared to its area of cross section, and if it is made with homogeneous, means same homogeneous isotropic material, that is taken as a bar. And the line passing through the center of the bar is known as what? Axis of the bar. This is the axis of the bar. Clear? So when this bar is struck, what happens? So definitely the particles of the bar comes in vibrating state. Definitely we can observe waves. Depending on the direction of the striking, sometimes these bars can produce longitudinal waves, sometimes these bars can produce transverse waves. So in this second part of first unit, we will discuss detailedly about how longitudinal waves produced in bars, what are the cases when bar is fixed between the two rigid supports, when one end of the bar is fixed and second end kept free, when two ends are free, when the bar is supported at the middle. During all these cases, we will derive the expressions for frequencies of waves. So first part is about longitudinal waves produced in bars. Just to listen carefully and remember, the topic which I am going to explain today is the very important long question in this part, that is longitudinal waves in bars. Here I am starting this part of waves. Clear? Right. So, first topic is about velocity of longitudinal wave in bar. Very long question, very important question. Velocity of longitudinal wave in a bar. Clear? Sometimes they will ask like this. There is another way to ask this question, that is derive longitudinal wave equation in a bar. So, anyhow, this question is a very important question, long question, number of times repeated in the annual examination. Just listen carefully. Right? To derive the expression for longitudinal wave, here I am considering a bar whose length is L and thickness is small a. This is a uniform rod, length is small L and thickness be small a. This is the rod having uniform thickness. Clear? Right. Let this end here I am representing as some x is equal to 0. This end I am representing as x is equal to L. Are you following? Just to see the diagram carefully. Let us consider what is the thickness of this bar, what is the area of cross section of this bar? A. Imagine this is A. And the length of the rod equal to how much? Small L. Let us consider two layers as A and B of the bar. Let this first layer is situated at x distance from one end. This second layer of the bar is situated at x plus dx from the fixed point. Clear? This is about the scenario. If the bar is striked, definitely bar comes in vibrating state, that is definite. So, we can observe some longitudinal waves. When longitudinal waves are passing through this bar, what is longitudinal wave? You have to remember what is longitudinal wave. When particles of the medium vibrates parallel to the direction of propagation, then the wave is said to be longitudinal wave. So, our discussion is about longitudinal wave. When this bar is struck like this, what happens? It comes in vibrating state. The particles of the bar vibrates like this, to and fro motion. When particles of the bar vibrating like this, what happens? There is some displacement of the layers. Let us imagine during the passage of this longitudinal wave through this bar, let A displaces from this position to this position and B displaces B to some B dash. Imagine like that, right? During the longitudinal wave passing, that layer A is changing its position from A to A dash, B is changing from B to B dash. Imagine the displacement of this layer due to this longitudinal wave. Here I am representing as some y. The displacement of this layer here I am representing as some y plus dy. Clear? Is that clear? Right. So, next I want to calculate the extension produced in the layers. Before that, just to observe what is the length of the element that I have considered here. What is the element I have taken here? AB. Original element is AB. What is the length of this element? Just to see the values in the diagram. This is x, A is at x distance, B is at x plus dx distance. Therefore, the length of this element will be dx. This distance definitely equal to how much? Dx only. Clear? Right, very good. So, I want to calculate the extension, I want to calculate the extension of the AB due to the passage of this longitudinal wave. For that, what is the displacement of A layer? Here I am writing point to point. Displacement of A is equal to how much? Y. Similarly, displacement of B, that I am representing as here from B to B dash, that is, this is A to A dash, this is B to B dash, which equal to how much? Y plus dy. Next, I want to calculate y plus dy by using Taylor series. Already we have used Taylor series in the first part of this unit, that is during the derivation of velocity of transverse wave. Already I have used Taylor series. What is Taylor series? Just remember the Taylor series. I want to calculate y plus dy. I want to expand y plus dy with the help of Taylor series. Since from Taylor's series, what is Taylor's series? F of x plus dx is equal to f of x plus f dash x dx, next f plus f double dash x dx square by 2 factor, like that. So, always in our physics we consider first two terms of the expansion. So, I am going to use Taylor series here to find this expansion, that is y plus dy. So, f of x plus dx is equal to f of x only, first term is as it is, plus second term is we have to differentiate this term, that is dy by dx, and multiply with dx. So, next term will be d square, third term d square y by dx square, dx whole square by 2 factor. Third term, next fourth term will be d cube y by dx cube, dx cube by 3 factor, like that. But always we have to consider the first two terms of the expansion, this one and this one. Is that clear? Right. I want to calculate the extension in the element. Therefore, extension in the element, extension of AB, right. So, after passing of longitudinal wave in the bar, what is the displacement of the second layer? This one, that is y plus dy by dx into dx. What is the displacement of the first wave? That is y. If I want to calculate how much extension of this layer, for that we need to subtract y from this value. So, finally we get the extension in the element as how much? Y. This is final layer, this is the displacement of the second layer, this is the displacement of the first layer. If I subtract, I can calculate extension of the given AB element as dy by dx into dx. If you are having any confusion, instead of d you can write as dou, partial differentiation. Somebody maybe gets confused, sir, I want to cancel this, sir. Don't do like that. Instead of d's you can write as dous. This is d only. Clear? I have calculated extension in the element AB. Just remember Young's strain. I want to calculate longitudinal strain. What is longitudinal strain? Just remember longitudinal strain. Longitudinal strain. What is strain? Change in dimension by original dimension. This is about longitudinal. So, change in length by original length. Original length. What is change in length? That is extension in the wire, the extension in the element, that is dou y by dou x into dx. What is original length of this element? Original length of this element AB is dx only. So, finally, I have calculated this longitudinal strain as how much? Longitudinal strain is equal to dou y by dou x only. Let this is equation number some 1. Just consider Young's modulus. What is the definition for Young's modulus? Since Young's modulus, generally Young's modulus is represented by y. It is the ratio between the longitudinal stress by longitudinal strain. Generally, what is stress? Force per unit area. What is area of cross section of this bar? A. Stress definition is similar to pressure definition. So, I think everyone is familiar with stress. Already you have learnt about stress at your intermediate level only. Force per unit area gives what? Stress only, right. So, next step will be y is equal to Young's modulus is equal to this numerator I am writing as stress F by A. What about strain? Already I have calculated dou y by dou x. Dou y by dou x. So, next step will be after cross multiplication F by A is equal, this numerator is equal to y into dou y by dou x. Dou y by dou x. Next step will be F is equal to y into A into dou y by dou x. This is the force acting on the layer, right, who is having displacement y. Let this is equation number 2. Just to write equation 2, for layer A. Just to concentrate on layer A. What is the displacement of layer A? Y only. So, how much force acting on this layer A by longitudinal wave? That I am representing as some F1 force, which equal to, simply I am writing this general expression for layer A. Y Young's modulus, this is constant. A area of cross section, this is also constant. Coming to this term, this is y only. Here displacement of layer A is y only, that is why I am writing as it is. Let this is equation number 3. While the longitudinal wave is passing through the B, its displacement becomes y plus dy. So, if I write equation 2 for layer B, what happens? The force acting on layer B is equal to y A, same values, dou by dou x, but instead of y we have to write as y plus dy. This is the only change. This is the only change you have to remember. So, next step will be y F2 is equal to y A is common. Just multiply this dou by dou x with the first term, that is dou y by dou x. Multiply this dou by dou x with the second term, that is dou square y by dou x square. Dou square y by dou x square. What is y plus dy? Before that we have to substitute y plus dy. Already I have calculated y plus dy. Already I have calculated y plus dy by using this Taylor series. Just to give the number for this Taylor series, let this is 1, this longitudinal strain be 2, and I am changing the equation numbers. Let this is 3. Write equation 3 for layer A, we get equation 4. Write equation 3 for layer B. What is y plus dy? What is y plus dy? That is y plus dou y by dou x into dx. Simply I am using y plus dy value. If you have any doubt, just write as since from equation 1, that is Taylor series. So, finally, here I am going to calculate force acting on layer B, that is F2 is equal to how much? YA, here we are having YA already dou by dou x. Instead of y plus dy, I have written the expansion I got from Taylor series. Just multiply dou by dou x with y, YA dou y by dou x. So, this is okay, plus multiply this YA dou by dou x with the second term. It becomes YA dou square y by dou x square into dx. right? Let this is equation number 5. So, how many forces acting on this layer A and layer B? Two forces, one is F1, second one is F2. Therefore, net force acting on AB element. How do we calculate net force? That is final force, second force minus first force. What is second force here? Already I have calculated F2 value, just substitute this value. That is this one, YA dou y by dou x plus YA dou square y by dou x square into dx. Coming to F1, what is F1 value? YA dou y by dou x. This YA dou y by dou x, YA dou y by dou x gets cancelled. Therefore, net force acting on the element YA dou square y by dou x square into dx. Let this is equation number 6. Just remember Newton's second law of motion. What is Newton's second law of motion? Since from Newton's second law of motion, what is Newton's second law? F is equal to ma. F is equal to ma. F is equal to m into what is a? A can be written as rate of change of velocity is called acceleration. So, acceleration can be represented in terms of displacement and time as dou square y by dou t square. And what about m value? What is m? I want to express m value in terms of volume and density. M is equal to V into rho. V is volume, not velocity, volume, into dou square y by dou t square. Just use density definition. Ratio between the mass to the velocity is called density of the given material. So, on cross multiplication we get m is equal to rho into V. I have used that expression. What is volume? What is volume? Volume means that is the volume of this element. How do we calculate volume of this AB element? Length into breadth. Area, length, that is dx. Breadth means area of cross section. A into dx. A into dx gives what? Volume of the given element. Instead of this V, here I am writing as A dx into rho into dou square y by dou t square. Let this is equation number 7. Just to see the equations 6 and 7, you will get the final expression. Since from equations 6 and 7 both represents the same value, simply you can equate RHS, that is y a dou square y by, I am writing this expression first, Newton's second law of motion I am writing as first, that is a dx into rho into dou square y by dou t square. Coming to this one, that is y a dx dou square y by dou x square. A dx gets cancelled. So, I want to calculate dou square y by dou t square. This term which equal to y by rho into dou square y by dou x square. Let this is equation number 8. And equation 8 represents what? Equation 8 is known as what? That is the general wave equation, general longitudinal wave equation in a bar. Equation 8 represents the general longitudinal wave equation in a bar. But our topic is about velocity of longitudinal wave in a bar. Just remember the general expression for wave. Since from general wave equation, what is general wave equation? That is dou square y by dou t square into V square into dou square y by dou x square. Already I have derived during the first part of this waves only. Let this is equation number 9. Just to see the equations 8 and 9. Just to compare equations 8 and 9 LHS are equal, you can equate RHS. So from equations 8 and 9, simply I am comparing equations 8 and 9. So you can calculate V value. How? V square is equal to Y by rho. So then what is the final expression? Velocity is equal to under root of Y by rho. This is the final expression. Let this is equation number 10. In this way you can calculate velocity of longitudinal wave in a given bar, right? So this expression is very useful while we are doing the problems. So what are the factors influences velocity of longitudinal wave in a bar? That you can write directly from this equation 10. Velocity depends directly proportional to square root of Young's modulus of the material. Velocity of the longitudinal inversely proportional to square root of density of the material, and velocity of longitudinal wave does not depends on the shape and size of the material. These are the three factors we can observe from this equation 10. This is the very important long question. Number of times this question asked in the annual examination. Clear? So derivation is a very important, and remember, if you draw this diagram, if you write all these equations, you will get full marks. Don't bother about theoretical part, just concentrate on equation part so that you will get full marks. So very important question, number of times asked in the annual examination. You have to go through this question, you have to practice this question so that you will get full marks. So tomorrow we will discuss another topic. Until then, bye bye.